Now that I've hopefully convinced you that finding communities in a network is a useful and noble endeavor, let's see if we can figure out what a community really is. So, what makes a community? Perhaps it's mutuality of ties, so that everyone within a community has edges to one another. Maybe we don't want to be so stringent. Not everyone has to have an edge, but everyone should know at least K other individuals within the community. That's what makes a community. Maybe we're more interested in information flow. So for what we may want is that everyone is reachable from anyone else in a short number of hops, and we determine what that number is. And finally, maybe we don't want to set that it's, K other individuals that you know, but just that you know a certain proportion of individuals within the community. Okay, so before we get started, I think a very important point to note is that part of the reason why we see this community structure is because it arises out of a bipartite structure. A bipartite network is one where you have two different kinds of nodes. Say these are all individuals and these are all events. And so then you link all individuals who went to the same event together. So for example here, the first 4 individuals went to this first event, and that puts them in the same clique. For example, if the edge signifies did 2 individuals attend the same event, and this could then be embedded in communication frequency, etc. So yes, they probably all communicated because they went to the same event. So when we go about this task of discovering communities, what we may actually be finding are the different contexts, whether it's events or affiliations in clubs. For example, for boards of directors, do the directors sit on the same board? Well, then they're linked in the director network. So it's something to keep in mind, right, that this one mode representation of who talks to whom, in this case for social networks, is really an embedding of sorts of a more multidimensional network that exists out there. And so we're recovering some of it by doing community finding. Let's look at the first definition, that everyone should know everyone else within the same community. This is the definition of a clique. It's a fully, completely connected subgraph. And when you look at the cliques, they can overlap. So here we have 2 cliques, each with 3 members that happen to overlap. Within the clique, everyone knows everyone else. It's just a closed triad. Here we have a clique of size 4. Again, each of these 4 individuals knows the other 3. Let's go back to that community structure we saw in the opinion formation example and see whether we can figure out how common cliques are within networks with community structure as opposed to the equivalent Heuristics random graph. So we can find it. Okay, great. So here we are, and all you're going to be doing, I guess not that. Okay, we're going to set up here, and we're going to, you can lay out the network, and then we're going to highlight the maximal clique. So here's the Heuristics version. So we can set up some more, highlight the maximal clique, or we can see the familiar community structure and again look for a maximal clique. And you can click this multiple times if they're the same, multiple cliques of the same size. Okay, so that's your quiz question. And moving on. So how meaningful are these cliques? For one, they're not really robust. So let's say 2 people are not friends or didn't talk at the party or something like that. that invalidates that whole clique. It's no longer a clique, and maybe you then miss the fact that it's really a community. The second part is that maybe it's the clique itself is not that interesting because everyone's connected to everyone else. You don't have a densely connected core and then more peripheral individuals. All you have is that densely connected core. And there's no point in running any centrality measures on this because everyone has the same degree, any other centrality measure you would like to apply. And finally, how cliques overlap may be more interesting than simply the fact that they exist. And in the last segment of this week's lectures, we'll talk about a clique percolation algorithm that takes advantage of exactly this fact. So let's be a little bit less stringent. K-cores say that unlike cliques, you don't need to know everyone in your K-core, you just need to know K of them. So looking at this network then, can you tell me what is the K for the core circled in red, or depending on your quiz question, what is the K for the core circled in blue? Indeed, you should have found that this is a 3-core, so every node on this side is connected to at least 3 other individuals within that same 3-core, and the one on the left is a 4-core because everyone's connected to at least 4 others. What makes K-cores also not that robust is this example down here where you have a node that really should rightly belong with all the other nodes in this 4-core, but it has only 2 edges. And so it can't be part of a 4-core. It would need at least 4 edges to do that. And so the next core that it can join is a 2-core that then envelops both of these communities. And so we would incorrectly, really leave this one out if we were looking for kind of meaningful communities. Of course, if you want to stick to the definition 4-core or bust, then yes, that node should be left out. But is that really what you want to get out of your community finding exercise? As I mentioned before, sometimes you want to just look for potential for information to flow. In this case, we may just be interested in a set of nodes such that, for example, any node is reachable from any other node within two hops. And so in this case, these are two cliques because everyone can reach everyone else within just 2 hops. And there's some problems with this. The first is that even though 2 nodes, for example, these 2, may be reachable in 2 hops, that other node may be outside of this 2 clique, right? And so the actual diameter of this 2 clique is greater. Actually, it's this one. It's diameter 3, right? The longest path between any 2 nodes is called a diameter. And here, it's actually larger than the n of the clique. And it's also not so great that we've left this node out. So these n cliques can also be somewhat funny animals. The final definition we'll examine are p cliques. This is where instead of saying you have to know k of the other individuals, you have to know at least the proportion p of the individuals within the cluster. So all of these methods that we talked about really focus on networks that don't have any sort of distinction between the edges, so all edges are weighted equally. This is kind of the minimum information scenario, and you're actually better off if you know how frequently individuals communicate, because very likely those within the same community are talking more often. And so if you're lucky, you can actually just use this information directly. For example, you could eliminate ties that are not reciprocal. So going back to the dining table partners data set, you could just say, well, if two girls did not reciprocally name each other as someone they wanted to sit with at dinner, well, then let's toss out that edge. And that will reduce the network, and you'll be able to see more coherent communities. Another thing that you can do is just keep all the edges above a certain threshold and throw out the rest. So that's what I'm going to attempt to do now in Gephi. These are political blogs from a long, long time ago. I was studying these, and let me just try and fit all of this on my screen. Great. So I sort of artificially removed the weights and any sort of partition just so you can see that, you know, and of course, if this wasn't laid out, you may have trouble seeing that there are two communities in here. In any case, this looks very densely connected, and it's not that clear that, you know, these kind of clique algorithms, they would probably lump everything together because it is just such a dense network. All of these political blogs are mentioning each other left and right. But let's see if we can tell left and right apart. So what I had done was sort of artificially remove the weight. So what I'd like to do is move the mentions into weight. So I want to take mentions and copy data from mentions into weight. Okay. Hopefully that worked. So if we go back to overview, great. So now we can see that, in fact, what we perceive to be the two communities, and actually let me color them now. So you have the conservatives and the liberals, and you in fact do see that the conservatives tend to talk to each other more often, and the liberals tend to talk to each other more often. And now we're ready to apply a filter. So I'm going to do that. And we can increase the filter. So for example, maybe they have to have mentioned each other at least 4 times. And this already thins out the network a lot, but still you have most of the liberals connected, most of the conservatives connected. If we increase this a little bit more, a little more, come on. Okay, for the most part, with the exception of, let's see who these people are, Talking Points Memo and Whizbang blog, who mention each other a lot. For the most part, you see 2 separate communities, and I didn't apply any sort of community detection algorithm, no cliques, no K-cores, no nothing. All I did was threshold the weights. But in the next segment, we'll be talking about what you can do when you don't know the number of communities there are, whether they will be cliquish or not. How can you automatically, in a systematic, principled way, discover community structure, especially in large networks? So that's what we'll do next.